Welcome, this is lecture 2 of Machine Learning and Bayesian Inference. In this lecture I want to do three things. The first is just review the material that I did introduce in last year's course on the subject of supervised learning. The second is introduce some other forms of learning that AI concerns itself with, because it's not all supervised learning. And the third is just to introduce some notational material, because there is going to be quite a lot of notation involved in this course, and I want to set out some other standard stuff from the outset. So this is where I started last year in talking about supervised machine learning. I will recap, starting with a simple example. You've already met Evil Robot. It turns out that Evil Robot is terrified of kittens. He therefore wishes to make himself a kitten detector. And Evil Robot thinks that one way of doing this would be to use his sensors to measure two input variables, two input features. And those two input features are cuteness and furriness. And he has collected some data to go with some of the things that he has come across while doing his evil thing in the world. And that data is shown on this slide. And as you can see, there are various things that he's come across, and he has measured their cuteness and their furriness and plotted them on a two-dimensional graph here. So what can you do with this? Well, hopefully it's sort of clear how things have worked out. Up in the top right hand corner we do indeed have some kittens, which are both cute and furry. But we also have some other stuff. There's this chap down here who is neither cute nor furry. God knows what this is. This bloke seems, I don't know. Do you think he's cute? Who knows? But he's definitely not furry. The kittens are up here, and in the middle you've got some weirdo, and a sort of not particularly cute dog, in my opinion. Okay, your opinion of the dog may differ. Who knows? Now, having done that, it seems sort of fairly clear that Evil Robot might decide to detect kittens by choosing this particular part of the plane that's now marked in blue and just saying that, well, anything that occurs in there I'm going to decide is a kitten. And based on this data that he's collected, this training data, that may or may not work just completely fine. However, we would expect in practice that it's not going to work all the time. Here we now have this wee chap. This little puppy is both cute and furry, but he's not a kitten. Unfortunately, he now becomes an error when Evil Robot tries to classify him. And similarly, there will be occasions where Evil Robot comes across a cat that is, in some sense, not sufficiently cute and furry and therefore will be misclassified. And we have some examples of that here as well. But that, in a nutshell, is what this supervised learning idea is trying to do. It's trying to come up with a way, based on some experience so far, of being able to draw a distinction between one or more classes of thing in such a way that when you come across things you've never seen before, you often get it right. And that's called generalization. That is machine learning in a nutshell. That is supervised machine learning in a nutshell. Now this is essentially the same bunch of notation that I used in last year's course in developing the idea of a perceptron and of a multi-layer perceptron. So let's just recap this briefly. We generally have a bunch of vectors of features, in this case m, and I will generally always use m to denote the number of training examples and n to denote their dimensionality. Vectors are usually real valued. They don't have to be. But it's a nice way of keeping all this uniform for now, just to assume that they are. Each has an associated label, y. So here we have m labels y paired up with the examples. So a single training example is vector x sub I and y sub I. We're generally going to denote a single training example. It's going to be, well, the ith example is going to be the xi paired up with its label yi. Our underlying aim is to use this finite collection of information to try and find a hypothesis, h, that is a general mapping from n real numbers to some label. Okay, big Y here is being used to denote the space of possible labels that I'll come back to in a moment. And the trick then, of course, is that because that's a function, it's a general relationship, we can give it any input x that we like, even one that we've never seen before, and we hope to end up having chosen h in such a way that it makes a reasonable guess for the correct value of y. H can be drawn from a collection of possibilities, sometimes called a hypothesis space, either directly using some training algorithms or using the kind that we've already seen, because that space is parameterized. And we have a bunch of weights, which I'll generally denote using bold W, meaning a vector of real valued weights, which implicitly defines this function h that goes with it. And when that's the case, then h will usually have a w associated with it in some sense, as well as its argument x. There are then essentially three scenarios differentiated by what kind of outputs y you allow. If y is itself just a real number, then we're doing regression. This might be the case if, for example, to use an earlier example from lecture 1, we are interested in the oil pressure in your jet engine and you're trying to predict what it is. Oil pressure would be a real number. It may be constrained within particular bounds, in which case we can account for that, but for now we could just assume that it's a real number. Second possibility is that y could be one of k possible values, denoting k possible categories. We might want to say that the oil pressure is low, low to medium, medium, medium to high, high or critical. Or in a lot of what we're going to do, in order to keep it notationally straightforward, is just have two categories. We're going to look at two-class classification problems. But we're also going to look in quite a lot of detail at the final possibility here, which is, in a sense, somewhere between the two. Because we want to put probabilistic interpretations on things, one of the things that we're going to be doing is to have a hypothesis that outputs a real number that's in the interval between 0 and 1. And then we can interpret that as a probability. Okay? And we'll typically interpret it as the probability that you are in one or the other of two possible classes. The output of your classifier will be a probability, and if it's 0.9, it's very likely that you think that your input is in class 1. If it's 0.1, you think it's very likely that your input is in class 2. If it's 0.5, you're not really sure. And this is one of the selling points. Okay? At that point, you can talk about uncertainty in the prediction that you're making. And that's one of the things that the Bayesian interpretation is going to allow us to do. Now, I mentioned last year that you can, to a large extent, think of supervised machine learning as essentially a form of curve fitting. The reason for that is that you can think of it like this in the context where you have one input, which is on the x-axis. That's just instead of a vector of x's, we just have the single x now. And on the y-axis, we have the output y. Okay, so we're just learning a function that takes an x and predicts a value y for it. Now what's going on here is straightforward. It's exactly the sort of curve fitting that you will have been familiar with from your earlier education, I would imagine. But I should go into a little bit more detail about what I've actually done in order to make this diagram, because it's going to become important later on. Here we're doing regression, we have a single feature, and we're trying to predict a real number. The red circles here denote some training data that I've generated. The blue dotted line is essentially the correct relationship between x and y that you are trying to identify, but which you never actually get to see. The game here is that, in fact, those red circles have been generated by initially finding some points that are on that dotted blue line, and then adding some noise to the y-axis. So those red circles are exemplars of this actual relationship that we want to be able to identify, but we never actually get to see. They are noisy, so that real relationship has been, in a sense, partially hidden, and we want to take those red examples and use them to try and guess what the blue line is, the dotted blue line is. Here I've then actually tried to do that using the kind of thing that I spoke to you about again in the course last year. Each of the other panels here is labelled with the degree of the polynomial that I've allowed myself to use in fitting that data. D is 1 means I'm just fitting a line, D is 2 means I'm fitting something linear or a parabola, D is 3 means I'm fitting any polynomial relationship between x and y up to degree 3. I'm choosing a polynomial in order to minimize the sum of squared distances between the actual y values in this data and the y values that are predicted by the polynomial. So the sum of squared errors was introduced last year, and it was introduced on the basis that it seems like a sensible thing to do. And indeed it is. But one of the things that's going to come out of putting this in a probabilistic context is that it's going to uncover the fact that using sum of squared errors actually hides at least one quite important assumption. Now, having said that, we can see something reasonably interesting about what's actually ending up happening here. If we use d equals 1 and we just try and fit a line to this data, we get something that doesn't fit particularly well. That much is clear. And similarly, if we use d equals 2 and we fit a parabola. But then we hit d equals 3 and all of a sudden we get almost a perfect guess for what the underlying relationship is. If I tell you that the underlying relationship is itself a polynomial of degree 3, maybe that doesn't come as quite such a surprise, and the reason that we don't quite identify it perfectly is that there is some noise in the training data. Now, one of the key things that I impressed on you last year is that this doesn't mean that you just use the largest degree of polynomial possible, because for d equals 7, all of a sudden we've suddenly got a big problem here. If we try and use our polynomial, the yellow line, to predict data that would be generated by the dotted blue line, and if we go up to d equals 10, then we can see that we're also getting some fairly major problems here. Now, that seems to imply that if you allow your choice of relationship here to be too complicated, you're going to end up actually learning to try and fit the noise and not the underlying relationship that was used to generate this data. This is called overfitting. So there's an interaction, in fact, with this problem between what the underlying relationship is that you're trying to identify, how the training data has been generated from that relationship in terms of its noise characteristics, what functions you're allowing your learning algorithm to select in order to fit that data, and how exactly you choose a particular function to fit the data from your allowable collection. And the interaction between these things has been studied in fairly extraordinary depth. I will not have time in this course to tell you about computational learning theory or the use of statistical physics in analysing generalisation performance or any number of other interesting things. But the take-home message really from this slide is that you can think about supervised machine learning in this context, but then you immediately have to remind yourself that you're not going to be doing it with just one input variable. You may well be doing it with 1 million or more. And at that point, actually visualising it becomes completely impossible. Here we can visualise what's going on, but in real circumstances, the complexity of the models that we're trying to deal with in practice is much, much higher, and that makes this problem much, much harder. Now this slide is just summarising really what I've said about exactly what the training algorithm is in making that example. I'm fitting a polynomial of degree d, and I'm fitting it using this chap here, which we've seen before, the sum of the squared errors on the training examples, which just means whenever I have a training example, the ith training example, xi, yi, I put the xi into my prediction for what yi should be. That's the actual value of yi. I take the difference between them and square it so that I get a positive number, and then I add all these values up over all the training examples that I've got to get a measure of error. And I try to choose w, the weights, okay, or if you like the parameters in this case of this polynomial, in such a way that e of w is minimized. Okay, that's what I've done in order to generate this, and that's what we did when talking about backpropagation and multilayer perceptrons in the course last year. Now, the fundamental building block that we spoke about earlier is the perceptron, or just, if you like, the linear classifier. Okay, perceptron is an interesting piece of nomenclature that's been around for a very, very long time, but really this is just a linear function that can put its output through maybe a nonlinear activation function. But let's just remind ourselves of what's going on here. Real problems have more than one feature. Okay, we don't just measure cuteness, we measure cuteness and furriness, and maybe a whole bunch of other stuff as well. Okay, so we need to move to a situation where we can construct functions that have multiple features as inputs. In this case, n of them, x1, x2 up to xn. And Perceptron just makes a linear weighted sum of those, and it also has this extra input set of 1 here, which plays the part of being a bias. Sometimes you'll see a slightly alternative way of writing this, which is that instead of having the linear part written as in the node here, we would actually write it as the sum for I equals 1 up to n, not 0 up to n. Again, it's a weighted sum, but we would then have w0 expressed as a separate bias weight. Okay, the construction of having an extra input that's always 1 is just to make this more easy to write in a notational sense, but we'll come on to that in a minute. The trick then with a perceptron, and these are or have been widely used as just individual machine learners throughout the history of the subject. There again is to choose those weights in a way that minimizes some measure of error over some collection of training examples. Now, it's very easy to dismiss this little guy, the perceptron, as being far too simple to ever work in practice. Well, you might be surprised. I'm going to give you 2 reasons that you should know how to train a perceptron. The first is that there's a lot of evidence that outside the realm of having huge quantities of data to play with, which can be the case, particularly if it's expensive and hard to gather, simple classifiers can do remarkably well. It is generally worth trying a simple classifier before you try a complicated one, particularly if you're in the domain where you don't have a huge quantity of data to play with. But the second, and I think more important and more interesting reason that these are something you need to know about, is that with a few tweaks allowing them to do computations that are much more non-linear, they become much more powerful. But the underlying mathematics of how they work is still linear, and that's good because linear things are easy. If you make a couple of modifications to these guys and do something quite clever with the training process, you get something called a support vector machine. And these are essentially, again in the domain where you don't have huge quantities of data to play with, the state of the art. Okay? You can make arguments one way or the other about what is state of the art. The fact is that for any given data set, the only way you know what's going to work best is to try a bunch of things on it. But there are a small bunch of things, including the support vector machine, that you will probably find out are the set you need to try, and one of those will be your best bet. Okay, so support vector machines are powerful and effective, and you get them essentially by doing just some very clever modifications to this perceptron. Okay, so don't write this one off. Now, the actual training algorithm that I talked about last year is something that we're going to move away from for most of this particular course, although it's an approach that's very important, and it was gradient descent. If I take my perceptron and I say, okay, well, this guy here is generally called the activation function. Okay, what comes out of the linear part is A, the activation, and we can put a nonlinearity on the output of this thing in order to make it into a classifier, or to give it a probabilistic output, or we can have no activation function at all if we're going to do regression. If I do in fact do that, if I make sigma just the identity function, then my error, if I want to keep talking in terms of the sum of the squared errors, takes on this nice format here. That is because a weighted sum can be written as an inner product. Okay, so you need to remind yourself at this point that if w and x are both vectors, then the inner product, okay, if they are n-dimensional vectors, is just the sum of the corresponding elements. Okay? Hence, we get this nice representation for the hypothesis as a function of w, its parameters, and also its input x, in this case the ith x in the training set. And this is just the sum of squared errors again, and my suggestion for a training algorithm last year was that we do gradient descent, which means that we start in some random place with a random weight vector, and we do sequential updates to that weight vector each time taking a little step in the direction of the negative gradient. So E of w is a function of w, its derivative with respect to w tells you its gradient, and if we take steps in the direction of the negative gradient, we hope that we're just going to go downhill and eventually find a w for which E of w is small. And we have lambda here, which sets the size of the steps that we take. Now, that's gradient descent, and in its most simple form, the one I've just presented to you, again, you can illustrate it very nicely. Here in 2 dimensions, we have a function of 2 variables, x1 and x2. I apologise, it would have been clearer if I'd have made those w1 and w2 because we're talking about weights. But hopefully you can make the mental shift. Here I'm trying to minimise f of x, and I'm doing it using gradient descent. And here, if I use a carefully chosen value for the step size, I can see that starting from a random point, I make a nice smooth progress down to the pair x1, x2 that minimises f of x1 and x2. But that if I get my step size wrong, as in the 4 panels on the right, things may be rather different, and in particular, if I make my step size too small, my convergence is slow, and if I make it too big, then I can get all kinds of horrible oscillatory behavior. Okay, but that is a general method for minimizing a function simply by taking small steps in the direction of its negative gradient. Now for a perceptron, when we're doing regression, this is easy. Again, this is something that I derived in the course last year, so we're really just still on revision at the moment. The derivative of E of W with respect to an individual weight, okay, the jth weight in the weight vector bold W, is something that I get just by differentiating with respect to that jth weight. And that's straightforward. I've written this out in full essentially in the first line. In the second line, I exploit the fact that differentiation is linear, so I can take the derivative through the summation. Okay, then I have a function of a function. Okay, I actually want to do the derivative of this guy, so it's twice the thing in brackets. That factor of 2 cancels out the half, and then I need to differentiate the thing in brackets. Y doesn't depend on Wj, so it disappears, and I just need this derivative here. Okay, and how's that going to work? Well, if I go back to what I just demonstrated about that inner product, W transpose X, okay, if I write that out in full, I have W1X1 plus, at some point, WJXJ appears in there, and then it continues on up to WNXN. Well, if I differentiate that with respect to Wj, the only term that actually depends on Wj is this one, so all the other ones go to 0, and the derivative of this term is just xj. So, what I end up with here, in this case, is the jth element of the ith training vector. Okay, so that gives me a computation of the gradient of the sum of the squared errors, E of W, with respect to W, for a perceptron. The simplest learning algorithm you can really possibly imagine, I think. And what I then did in last year's course was extended this to the multi-layer perceptron. So the multi-layer perceptron is a beast that's been around for a long time. It was the centre of an earlier hype cycle of artificial intelligence in the 1980s. People were very excited about these, and you can actually get a long way with them. And they are, of course, still used as a particular building block in the whole deep learning enterprise as it continues to develop. Here, each of these nodes is itself now a perceptron, but typically with an activation function attached to it, because, well, if you put a whole bunch of just linear things together like this, you end up with one big linear thing, and that isn't giving you anything much more in terms of computational ability. So each of these is now a perceptron, typically with a nonlinear activation function. And every one of those arrows has a weight attached. And once again, your input features come in here, and your prediction. Let's get that right. Your prediction comes out here. And I talked about the backpropagation algorithm. Okay, so these guys can be trained using gradient descent, and the backpropagation algorithm is, if you like, just a systematic method for computing the partial derivative of your function of error with respect to the weights. And then you can do gradient descent, and that allows you to train multi-layer perceptrons. Now, it is certainly the case that you probably wouldn't do that using simple gradient descent nowadays. You're probably using something like the Adam optimizer, being probably the current most popular alternative. But there are huge piles of literature about how you minimize functions in this way, how you take functions like e of w and minimize them with respect to w, using a whole plethora of different techniques. And I made some mention of this last year, and if you ever get into this stuff really in anger, you will no doubt find an absolutely massive literature on the subject. But at the moment, the one of choice seems to be the atom optimizer, but I'm not going to talk about that in detail. But it's important to remember that backpropagation is just a method for computing the derivative, dE by dW. Okay, and it generalizes and scales up to all manner of other things, but the underlying idea remains the same. I'm going to emphasize that even further. Okay, backpropagation is just a method for computing a derivative. You need to do that because you're doing gradient descent, and you need to do it even with the more recent and modern approaches to this kind of function optimization, because they all tend to need a derivative. Some will need the second derivative, some will not. Okay, there's a big literature on this subject, but a lot of methods for doing this kind of optimization of the function e require you to be able to get a first derivative, and that's what backpropagation gives you. Now let me just briefly mention some other kinds of learning. The first is unsupervised learning. And the question here is, what if I just give you a bunch of feature vectors that haven't got any labels? I just give you m vectors. On the panel on the left here, I've just given you m vectors. The question is, can you identify any structure in that? This field also tends to be called clustering, because what we're trying to do is identify an underlying bunch of populations from which we think that this data was generated. And on the right, I've run a simple clustering algorithm, and it's suggesting to me that those are the three clusters that we used to generate the data on the left. Now we can start simple with such algorithms, and in fact I am going to talk about this in the course, but I'm only going to talk about the case where we assume how many clusters we think we're trying to identify from the outset. Remember again that in practice this isn't just in 2 dimensions, it's in a very, very large number of dimensions, and it's not quite so obvious how you would assign things to clusters in that case. But one of the nice things that the Bayesian approach does give us, if we go beyond this course, is, for example, a bunch of ways of inferring from the data not only what the clusters are if you assume you know how many, but how many clusters there is in the data as well. Okay, this is another of the payoffs that we can get with this kind of approach. Here is another kind of learning. This is called semi-supervised learning. On the left, I've given you some supervised learning data. Okay, there is data in 2 dimensions here from 2 classes. Data from class 1 is the blue crosses, data from class 2 is the red circles. What I've done in the right-hand panel is to augment that with a whole bunch of unlabeled data. So this is kind of somewhere between supervised and unsupervised, hence the name, semi-supervised learning. The reason this is important is that it turns out that getting hold of unlabeled data is often much, much easier than getting hold of labeled data. If you take the standard example of medical diagnosis, getting hold of patient records may not be too hard. Getting hold of patient records that have been labelled as to whether or not a person has a particular condition is much more tricky. Now, you might want to ask yourself whether the addition of those light blue dots, the unlabeled data, to the labelled data, as we see it in the right-hand panel, actually gives you any insight into how that labelled data was generated. It may do. We'll come back later to exactly how I did that, and I think it will look an awful lot clearer, but maybe it's just something to think about for now. The other kind of learning that I should mention, because it is rather coming into its own at the moment, is reinforcement learning. In reinforcement learning, we're not learning from labelled examples. This is class 1, this is class 2. We're learning from rewards. Okay, and this form of learning is much more grounded in the kind of problem description that you remember from AI, in terms of being much more like intelligent search or planning. In this context, we once go back to the idea of having states and actions, and of moving between states by applying actions. But we have an extra element now, which is that when we perform an action and move to a new state, we also get a reward, which can be negative. It can also be a punishment. Now, there can be probabilities associated with which state we get to when applying an action, and also what reward we get. And we have no knowledge in advance of how the world works. All we can do is try things out and see what states we get to and what rewards we accumulate. But the idea is to learn a policy, which is some mapping from a state to an action. And we want to learn a policy so that when we apply the actions that it tells us to apply sequentially, we maximize the amount of reward that we get over time. Okay, so it's a little bit like planning, and it's a little bit like planning that's had uncertainty attached to it because of these probabilities that are involved. And it turns out to be extraordinarily useful and effective in some of the more recent approaches to doing learning within AI. Now, while I won't, again, have time in this course to talk about reinforcement learning, much as I'd love to, because it's a brilliant subject, what is important to point out is that quite often it requires some other form of learning as a subsystem, usually some form of supervised learning. Okay, you need a supervised learner in order to implement quite a key part of the overall reinforcement learning system. Okay, so we're still learning something that's going to be useful if you go on to look at this kind of stuff in more detail. Now, the last thing for this lecture is just to introduce some notation. I'm going to talk about vectors of reals a lot. Vectors of reals would be bold lowercase characters, and r to the power of n denotes the collection of all possible n-dimensional real valued vectors. And similarly, if I write r to the n by n, that's the collection of all real valued matrices with m rows and n columns. It's conventional within this field to assume that vectors are column vectors. Okay, transpose is denoted using a capital T, and that is why you will often see vectors written in a transposed form. Okay, because once you want to get them on a row within the text, you need to turn them into a row vector, and by convention they're column vectors. That, as far as I can tell, is something that's been imported from the signal processing literature several decades ago, so don't blame me for that. It's just a standard. For a matrix that's m by n, okay, we can write it in terms of its elements, just like this. There should be nothing new here for you. This is all really just harking back to NST maths. But I may use this star notation to denote a specific row or a specific column. I'm not going to use that very much, but occasionally it comes in useful for picking out a specific row or column of a matrix. If I've got m vectors, then the jth element of the ith vector is denoted like this. And we can do all sorts of notational gymnastics in terms of how we then write vectors and matrices. So here X has a bunch of rows, X1 transposed down to Xm transpose, and we can write them as individual elements by picking the jth row of the ith vector where necessary, and we get this kind of arrangement here. Or we can write it in terms of column vectors, like this. Okay. this is really horses for courses. And I can tell you in advance that there are parts of this course where you will have to spend a bit of time getting used to this kind of wrangling of vectors and matrices. At some point we're going to get into the fact that you need to be able to differentiate quantities that involve vectors and matrices, sometimes differentiating with respect to a vector or a matrix. This does unfortunately involve some kind of notational pain and suffering, but I'm afraid if you want to do work in this area and really understand and develop new algorithms and understand how they work, it's kind of inevitable. The identity matrix is its usual self, okay, it's I, and its size is usually inferable from its context. Inverse is written by superscripting -1 and determinant by putting the mod symbols on. Yes, I'm afraid I will need to talk about determinants. I suspect that might be something you've forgotten about from NST Maths, so that's something to go and revise now. Now, I use a fairly standard notation when dealing with random variables. A random variable is a set of values, and the random variable itself is conventionally written in uppercase, whereas the specific values that it can take are written in lowercase. So if I have a random variable big X, it may take values in some particular set. The probability of a specific value should then really be written the probability that the random variable takes some particular value, but it's often abbreviated just to the probability of that value. Okay, hopefully that won't cause any confusion. The expected value has its usual form. Okay, the expected value of the random variable. In this case, I'm only talking about discrete random variables here. We will have continuous ones as well, but really the hint with this slide is, once again, if you've forgotten this kind of notation, go and remind yourself about it. The expected value is taken by summing over all the possible values of the random variable and taking the value multiplied by its probability. And I may also write that in this slightly different notation here, which hopefully makes sense. And everything can be extended to vector-valued random variables in the obvious way. You're then having multiple sums or multiple integrals, but the fundamental manipulations and calculations that you do are really the same. Again, there's some guidance in the handout that I talked about in the first lecture as to how to think about that kind of stuff. So using that notation, inputs are in n dimensions and will be denoted by vectors of features. Okay. Again, just going back to the standard example I used last year, a particular feature vector, if you want to use the medical diagnosis example, would be what you get if you take the information you have on a person, collect all of the interesting things about them together that you think you might need in diagnosing them, and collect them into a vector. Okay, the label is then, do they or don't they have the condition? What is the probability they think they have the condition? Do they have one of this collection of k possible conditions, or whatever? The training sequence has m things in it, so you can denote that as a matrix where each column is the feature vector for a single training example. And the labels will generally just be collected together into a vector as well. Okay, so what you have on this slide is essentially just saying that whereas we used to write a training set, I think the notation I used last year was S, and I would pair these guys up. Now we can just collect them all together into a single matrix and a single vector. Okay, now we can say that S is just our pair as defined on this slide. Okay. Now, there is a reason for this. We're about to start looking at some learning algorithms within basically the linear case. And it turns out that with some linear algebra, this allows us to express those training algorithms much more succinctly than if we'd used this approach. Okay. So in general, for regression problems, we have the possible values for outputs are just the reals. For classification problems with two classes, I will say that our possible outputs are this Boolean set B here. Now, sometimes this set B will be +1 or -1, and sometimes it will be 0 or 1. The reason that I use two different definitions for that, depending on what I'm talking about, is that some training algorithms are much easier to express with one than the other. Okay, so in particular, when we're talking about anything Bayesian, it tends to be nicer to express the two classes as 0 and 1. And when we're talking about SVMs, it's nicer to talk about the two classes being +1 and -1. Okay, that's the only reason that that notation will vary. And for classification problems, again, if we have k classes, then we have a set with k possible indicators for those classes in it. And finally, I will sometimes also revert to the older way of talking about the training set. The reason for that is exactly the same. Sometimes it's just more convenient, but sometimes representing that as a matrix and a vector is more convenient.